My greetings to you all. We are now to the last class for this week, which is module 5, and so far we have seen about domain, different types of grid, how to obtain Taylor series expansion, from Taylor series expansion how to obtain different difference formula and higher order accurate scheme, and how to obtain finite differential scheme on non-uniform mesh. Also obtaining mixed difference formula for mixed derivative. Now today's class we will particularly see how to get higher derivative and getting finite differential formula by other procedure, particularly we are going to see by polynomial procedure. So, we had seen so far all this, and we also have equation with higher order terms. For example, if you consider vorticity transport equation or vorticity stream function formulation that we had seen last week, it has a fourth order based on stream function. So, we should know how to evaluate or how to obtain finite difference formula for any order as well. And this we had seen towards the end of last class. We repeat here for the sake of continuity. So, Taylor series expansion is written for 3 different spacing, f of x plus delta x, f of x plus 2 delta x and f of x plus 3 delta x. By now you are familiar how to write Taylor series expansion in any direction, that is either forward or backward. You are also familiar with the procedure to get any difference formula. So, writing the equation for 3 different spacing x plus delta x, x plus 2 delta x and x plus 3 delta x, and what we are interested is the last term, that is the third derivative term, dou cube f by dou x cube, and that term is there in all the 3 equations, equation 1, equation 2 and equation 3. So, we have to do some kind of arithmetic operation manipulation to get rid of the term first derivative as well as second derivative. So, we basically do 2 arithmetic operation in the beginning, considering equation 1 and 3. So, multiply equation 1 by 3 and subtract it from equation 3, which is actually for f of x evaluated at x plus 3 delta x. So, if you do that, you get this equation 3 times f of x plus delta x, that is the first equation, and this is the third equation term. So, we have a term on the left hand side, remaining term on the right hand side. You can actually see term by term and verify this expression is correct, and we number this equation as 4. We do one more operation, that is multiplying equation 1 by 2 and subtract it from equation 2. So, we get f of x plus 2 delta x minus 2 times f of x plus delta x. This is coming from the first equation, that is why you have the coefficient 2 here. So, we said multiply equation 1 by 2. So, we have term on the left hand side and then remaining terms on the right hand side, and we number this equation as 5. Once again we have to get only third derivative dou cube f by dou x cube. We still have the second derivative term in both equation 4 as well as 5. So, one more small arithmetic operation, that is multiply equation 5 by 3 and add it to equation 4. So, if you do that, so the equation 5 you have a term del x squared whose coefficient is actually 1. So, if you multiply this by 3 and add it to corresponding term in equation 4, they both get cancelled, and finally you get, after rearrangement, finally you get expression for dou cube f by dou x cube, and which is given here, and you can recognize that it requires 3 additional points in the forward direction with respect to the function value itself. So, f of x is a point of interest, at I, and you need function values at x plus delta x plus 2 delta x and x plus 3 delta x, and this is forward difference formula of order delta x, and you can just follow this procedure as we did for first derivative and second derivative. You can also obtain backward difference formula, and it is also possible to obtain either forward or backward higher accuracy. So, in this case it is of order delta x. You can consider higher terms in the Taylor series expansion, replace them, do again arithmetic operation, follow all the algebraics carefully. It is possible to obtain any order of accuracy and in any direction, forward or backward. Next, we are going to see another procedure. So far, we have seen how to obtain difference formula only from Taylor series expansion, but there are also other procedure, polynomial approximation of a function, exponential fitting procedure, and there is also a different class of finite differential scheme, what is known as a compact finite differential scheme. So, as the name indicate, you are able to obtain higher order accuracy scheme by considering only less number of points, and there is a procedure available to get this higher accuracy scheme by considering only less number of points, and that is what is given as compact finite differential scheme. We are not going to talk about compact finite differential scheme. We will see how to obtain by polynomial approximation. So, the way to do is there are 3 steps. One is approximating the function f as polynomial. So, when you say polynomial, the obviously question is what degree it is required. So, depending on the degree in the polynomial, obviously one will get different accuracy scheme, and a polynomial will have a expression with coefficients, and you can obtain or evaluate the coefficient values, substitute in the function, subsequently to derivatives, then you will get difference formula. So, in this exercise we are going to demonstrate that procedure by considering second order polynomial, and that is shown here. Function f of x is approximated by second order polynomial as given here a x squared plus b x plus c, and this is a schematic graphical representation of the function, which is a point of interest f of I at I, neighboring points in the forward direction I plus 1, which is a distance of delta x, and I plus 2, which is a distance of 2 delta x from the point I, or it is a distance of delta x from the point I plus 1. So, if you evaluate that function, that is we had described quadratic polynomial function, evaluate that function at 3 different points that we have shown I plus 1, I plus 2. So, same function is repeated for different nodal points. F of I is a x I squared plus b x I plus c. Similarly, for f of I plus 1 and f of I plus 2. Why we want to do this expressing the function at 3 points? Because we have 3 coefficients a, b, c for the quadratic polynomial that we have considered a x squared plus b x plus c. So, you can immediately get an idea, if it is polynomial with a degree 5, then we need to get the expression or function value evaluated at 5 nodal points. Now, we need to evaluate coefficients a, b, c. So, first what we do, we find out these function values at specific locations. So, if you consider x of I as 0, because that is your point of interest, then x of I plus 1 is at a distance of delta x, and x of I plus 2 is at a distance of 2 times delta x with respect to I. So, it is to be clear, it is only at the distance of delta x from I plus 1, whereas it is at a distance of 2 times delta x from I. Once again, for simplification, we have considered only uniform mesh, that is why it is 2 times is coming here, and next we are going to see how to obtain for a non-uniform mesh also. So, if you substitute these values, that is x of I plus 1, x of I plus 2 in this expression, we get 3 equations for 3 coefficients a, b, c. So, on substitution, so x of I is equal to 0, first value, if you substitute in the first equation, a, b will go to 0, remaining term only is c, and that is directly related to f of I, as f of I is equal to c. Then we substitute for the second equation, f of I plus 1 equal to a del x squared, b del x plus c. Similarly, for third equation, a x of x at I plus 2 is replaced with 2 times delta x and square is there. So, it is a 2 times delta x squared plus b 2 times delta x plus c. So, if you solve, you already have value for c as equal to f of I, that also you can substitute. Then remaining 2 coefficients a and b are evaluated by suitable arithmetic operation between these 2 equations. And if you follow that procedure, you get expression for coefficient a and b, and that is what is shown here. Coefficient values b as expressed in terms of I plus 2, I plus 1 I as this way, and similarly for coefficient value a is expressed in this form. Now, come back to the polynomial expression that we have taken, quadratic polynomial function that we have taken. So, f of x is a x square plus b x plus c. So, if you substitute values for a, b, c, you actually have function evaluated based on function values in the subsequent forward points. So, you want first derivative, take the first derivative dou f by dou x and do the derivative on the right hand side, 2 times a x plus b, c goes to 0. Now, if you substitute for a and b in this expression from this expression that we obtained for coefficients a and b. So, you substitute b and substitute for a into this expression, we get dou f by dou x evaluated at x of I. This is our point of interest, and we already defined x of I to be 0. So, the first term goes to 0 and we have only b here. So, dou f by dou x evaluated at I is same as b, and that expression is here and that is repeated here for first derivative. Now, the question is how to know what is the order of accuracy in this scheme. We know from the Taylor series procedure how to obtain order of accuracy. Now, what we do in this expression, we substitute f of I plus 2 from the Taylor series expansion. Similarly, f of I plus 1 from the Taylor series expansion, f of I is same, that is on the right hand side, and we also know dou f by dou x evaluated by different procedure, by different order of accuracy and so on. So, we replace dou f by dou x and replace all this thing from Taylor series expansion and compare terms on either side, left hand side and right hand side. Finally, we get that this scheme is second order accurate forward difference expression. Though I have explained how to obtain the accuracy, it is not shown here. What is important is to know that this is second order accurate forward difference scheme, and you can also recognize immediately we have considered 2 neighboring points with respect to I, that is I plus 1 as well as I plus 2, and you can also recognize this expression from the first exercise obtained from Taylor series expansion. Now, we have shown for the first derivative dou f by dou x from this polynomial. So, if you do one more time derivative, then you will get second derivative. So, dou f by dou x is given here, do second derivative. So, dou squared f by dou x squared, and that is what is shown here. So, dou squared f by dou x squared is basically 2 times a, because the b also goes, and a is already here, that we obtain coefficients for a, and this 2 get cancelled, then you have only the remaining term for the coefficient a, and this is actually the second order second derivative forward difference formula obtained from polynomial procedure. And once again we follow the procedure of expanding this function from Taylor series on the left hand side and obtaining the difference formula from Taylor series and compare the coefficients, then you get an idea of order of accuracy of the scheme, and in this case it is first order accurate and forward difference scheme for the second derivative. Now, as we have seen before, we also have a situation of non-uniform mesh. So, we should find out how to do by polynomial procedure for non-uniform mesh also. So, function is given, again second order polynomial function a x squared plus b x is equal to c, and graphical representation for non-uniform mesh. So, I is a point of interest, I plus 1 is an immediate neighbor point which is a distance of delta x, and I plus 2 is the next neighbor point which is at a distance of alpha times delta x with respect to I plus 1, and at a distance of 1 plus alpha times delta x with respect to I point. So, we follow the same procedure expressing this quadratic polynomial that we have assumed at all the 3 points, then find out the procedure how to estimate these coefficients a, b, c. So, at x of I, which is a point of interest, the function is the x I value is 0, and x of I plus 1 is delta x, and x of I plus 2 is 1 plus alpha times delta x. Now, if you substitute in function, then we get expression like this, and we already noticed that c is related to f of I itself, and f of I plus 1 and f of I plus 2 are also expressed like this. We are interested to find out coefficient values of a and b, and c is substituted as f of I. Now, between these two equations we can solve and get a and b, and you get expression for b as shown here and expression for a as shown here. So, we use these values c, b and a and substitute in the polynomial expression that we have considered, and we are interested in the first derivative, then it gets reduced to 2 a x plus b. If you are interested in the second derivative, it gets reduced to 2 a. So, we substitute for a and b and substitute for a here. So, subsequently you get first derivative evaluated at x of I, because that is a point of interest. At I, x will have a 0 value. So, if you substitute that, the term is only b for first derivative, and that is shown here. Similarly, for the second derivative, it is 2 times a, and you evaluate, you already evaluated coefficient value for a, and you substitute, you get this. So, entire week what we have seen important aspect of CFD, first step, that is how to obtain finite difference formula by 2 different procedure, from Taylor series expansion procedure and from polynomial procedure, and first derivative, second derivative, third derivative, uniform mesh, non-uniform mesh, and how to obtain higher order accuracy scheme and so on. Thank you.